he said that Tripwire and other forensic programs weren't enough because you could just go to memory and start modifying things there, accomplish the same goals as replacing things on disk, and no one was looking in memory. Recently, the operating systems provided you with callbacks. There's specialized registers now. There's people using layered device drivers. We'll get into examples of all these and what they mean. Another way to hide your presence is to manipulate kernel data yourself. A couple years ago, I pioneered a rootkit called FU, and it used a term called DCOM, direct kernel object manipulation. With that, if you understand the structures within memory, you can just start changing them at will, and you'll completely disappear from all the higher level APIs that the operating system would expose to a developer in order to find files or find processes and so forth. I believe there's going to be some talks about virtualization and some rootkits moving into the virtualized world where they're in the hypervisor and therefore they can hide from the untrusted domains and subvert those. So a quick slide on hooks. There's several different types of hooks. An inline hook, also called a detour patch, is when you actually modify the binary function in memory. Normally this is to implement a jump or a call to your rootkit code. This is actually extremely similar to Microsoft's hot patching. They provide a nice little skeleton for you to be able to put an inline patch directly into their code. Makes it fun. There's also system call hooks. That's what historically memory altering rootkits did, like Hoagland's NT rootkit. It would replace calls in the system call table with pointers to the rootkit code itself, and therefore you gain execution, can manipulate the data. Then there's import address hooking. That is when you're writing a Windows program, you share certain DLLs because you don't want to write all the functionality yourself. You rely upon Microsoft and others. And at load time, the import address table patches up the function addresses that you need to use with where they're loaded in memory. So that's all done at load time, so you can alter that in memory and quickly gain execution flow control. IDT hooks, interrupt descriptor table hooks. These are used in rootkits like ShadowWalker and others. These are usually a little bit more advanced type rootkits. They're within the kernel and they're trying to gain execution when an interrupt fires. ShadowWalker used this technique in order to take over your page fault handler and then disguise the contents of memory. So a read to that region of memory would not display the rootkit code itself. ERP table hooks ERPs are IO request packets, and what they're used for is to, when a system call is made to like a write file or write to a socket and so forth, it flows through the system call table, but eventually it hits the driver that exposes that functionality. Every driver has an ERP table of about 32 functions that says upon certain requests, go to this address and execute. Therefore, if you can hook the file system driver, its ERP table in order to gain execution and manipulate file writes and so forth, or file queries. Callbacks are interesting because Microsoft has provided nice ways for developers to get called back upon certain system events on the computer. So you can say, hey, when a file access is made, I want to be called because I'm writing my own security software that's going to do some file filtering or maybe some inline encryption and so forth. Others are the Windows event, or the Windows messaging system is all based upon events. You can register to receive callbacks or notifications when a key is pressed or the mouse is moved. and so forth. So this is how almost all commercial keyloggers work. They register callback for the keystroke monitoring. There's object manager function callbacks. We won't go into too much detail about those. They're pretty low level, and they're not actually exposed through a nice API to you. In this protocol are more or less function callbacks where you can say, hey, I have my own protocol that's going to talk on the network, and therefore when a receive happens, I need to get called back when that transpires. And then I'm going to do something with the packet and pass it on, perhaps. So just the nature of the documentation of how these are implemented and the fact that they're standard makes detection very difficult, because now you have to determine, is it a legitimate piece of software that's registered this callback, or is it malicious? Special registers, you can set up debug registers so that when memory is accessed or a certain instructions executed at an address, you'll break into your debugger. The rootkit can set up its own debugger and get called that way. There's also the model-specific registers in the more recent architectures from AMD and Intel. These are equivalent to an interrupt descriptor table hook in many ways. You can register that, or you can overwrite the MSR register for sysenter, for example. In that register is just stored the address of the function that will handle the sysenter call. You can overwrite that with your own address in order to gain execution. that address will get called every time there's a system call from user mode to kernel, because it needs to alert the kernel, hey, I got some work for you to do, and I'm transitioning from user mode to kernel mode, and so you get called a lot there. There was actually a fairly recent example of this. I think the Rootkit rootkit used this mechanism in order to gain execution. Layered device drivers. These are also documented a way to gain execution control. Every single device on the system can be layered. So you can layer on top of the file system. You can layer on top of the keyboard driver. You can layer on top of the network device itself. And you'll receive these ERPs that we spoke of earlier before the actual device that should handle it. So it's a it's a nice way to gain execution control, and you can use this in order to hide yourself within the system. There's been a lot of, this is one way to implement keystroke monitoring as well, although not many people do it. And then there's direct kernel object manipulation, which I said a few years ago, like 2003, 2004, maybe a bit earlier than that. Anyway, I started that with the FU rootkit, and then recently it's progressed to the FU2 rootkit, which took another, not only did it unlink the linked list of processes, which is a data structure within the kernel, but it also took the additional measure of unlinking the handle tables and going after the handles themselves in memory, because there was a security product on the market that was using the handle table in order to find the hidden processes. So we continue to see evolution in the cat and mouse game. As soon as someone comes out with a better mouse trap, you know, there's someone that's figured out a way to break it. Although each attack gets more advanced, harder to detect, and makes your system less stable.
All right, so that's kind of the background on, you know, what's the state of the art, if you will, in rootkit techniques. Now, kind of turn the tables here now, and let's look at, you know, what are the ways that people are commonly using to detect these rootkits, and then talk kind of briefly about the remediation. One of the issues with rootkit detection is that it's pretty much like asking a crazy person if they're crazy. You really can't trust the answer. And so you need to find some way to correlate external or additional information and see if the answers that that crazy person is giving you are actually accurate. And so several of these techniques actually do that. The heuristic and behavioral detection we'll talk about, that kind of sets up a notion of what is normal for the system to be operating, and then looks for deviations from that. Integrity detection is pretty well known in the file system space. It's recently been moved into the memory space. Signature-based detection we're all familiar with. You know, that was kind of the core AV technology from years ago. And then the diff-based or cross-view detection, this is kind of what I just talked about, where you ask the crazy person a question, but then you ask another question in a different way, or you know, get the answer from some external information, and then compare them to make sure if they make sense. So kind of different examples on these, and we'll talk about each of these things in a little bit more detail. So as far as integrity checkers, there's actually, and so Jamie mentioned, he joked that he was going to introduce himself as Nick Petroni. Nick can't be here because concurrently with BlackHat is the Usenix security conference up in Vancouver. And Nick and I and Aaron Walters and Tim Frazier have a paper in that talking about semantic integrity, which I'll talk about in a second. And so Nick had to leave last night in order to get to Vancouver to present our paper there. But bitwise integrity is, you know, what we're all probably familiar with, MD5, SHA-1, SHA-256 hashes. They basically look at the scalar representation of the bits, whether they be on the file or whether they be in memory. You take a checkpoint or a baseline, a snapshot as we call it, and you know, you compare it at some point later in time, and the robustness of the cryptographic hashes should indicate if there's any tampering with those bits. Of course, if you're a cryptographer, it's early, I can't even talk yet, you'll know that you know, there are some collision problems with MD5, hints of same issues with SHA-1, and so you know, SHA-256 is kind of what people are looking at these days, but that's incredibly slow. Another approach, and this is the subject of our paper up at Usenix Tech Conference, or Security Conference, is what we call semantic integrity. And with this, rather than looking at the actual scalar values of the bits, what we're actually looking at are first-order predicate logic statements about the state of the system. And much like with a bitwise integrity system, you want that to remain invariant. You don't want it to change as the system's operating. The semantic predicates need to be the same thing. They need to be invariant throughout the correct operation of the system. And I'll talk about these in a little bit more. There are two things that we're aware of that are doing bitwise integrity. Our product, Joanna's SVV, which she's released, it's fairly well known. It's been used by a lot of people in the file system, like I said before. The really interesting thing about it is it's incredibly powerful, but it's also very, very difficult to do on a wide scale. And you know, when you start to take into account all the various changes that you may have in a system, you know, across all the systems that are being used, coming up with a set of hashes for that is actually fairly difficult. The other